Let's try trapezoid, which fortunately looks an awful lot like the left-hand rule. So we're simply just going to save this as a new file. We're going to save it as trap.m. And it's going to yell at us and say, hey, it should be called trap. So we'll fix that. Fix. Then we just go back to the math. So on our page back here, we wrote out the formulas for the trapezoidal rule and Simpson's rule. And so here, you'll notice everything in the left-hand rule was f of xi times delta x. We're literally going to create that line of math in MATLAB. We're going to say a half times blah, blah. The only thing that's going to be new, we've defined xi already. We're going to need to define xi plus 1. Not a huge shock. But we can do that pretty easily because we have a pattern to work with. The only downside is you can't put a plus inside the name of a function, or inside a variable name. There we go. So the first one, xi, starts at a and has I minus 1 delta x's to the right. I'm going to have one more delta x if I'm going one more step. So I just take away the minus 1, and that'll give me the two x values that we need. And then we literally say, I want 1/2 times bracket f of xi plus f of xi plus 1, the best thing we can write there, times delta x. So literally what was on the page is written here in MATLAB. So we're going to save this and we're going to test it. We're going to go back to our main script. We're going to evaluate the integral again, but now we're going to use the trapezoidal rule. And here we see the advantage of modularity. Everything's going to be the same in terms of syntax. And I'm just going to add a little more detail here. Left-hand rule error. And that's good. And we'll also show the trapezoidal error. And the first integral was I1. The trapezoidal rule, we're calling it I2. And so we're going to subtract that from the exact value. This is a case where we know from antiderivatives what the exact integral is, so we can compare. So mostly printing. In this code here, though, we see, hey, I'm going to evaluate an integral two different ways. Left-hand rule, the function 0 to L with n intervals. And then again, with the trapezoidal rule, the function f from 0 to L and with n intervals. So let's try running that. And lovely. So first off, what do you note about the relative errors of these two methods? Which one's better? Trapezoidal rule, exactly. Hey, why is it better? Because it's just more like functions. We go back to that picture. If we look at what functions do, functions change. That's what makes them hard to integrate, the fact that they're not constant. If I assume things are constant and build rectangles, that's never going to be as good an approximation as assuming it's changing. And I know the start and end points. A good guess is to guess that it's a straight line. And we can see that we get these are not even comparable errors. This is down to the second digit. This one's got 5 digits of accuracy right off the bat with this small number of intervals. And what's even better is we're going to boost the number of intervals here. We'll do a series of doublings again. 800, 1600, and we'll go to 3200. So not only is trapezoidal rule more accurate to start with for the same number of intervals, which isn't a huge surprise, there's what is, I think, a surprise, a bigger benefit. Every time we double the intervals, the error goes in half for the left-hand rule. What happens to the error every time we double the intervals for the trapezoidal rule? It goes down by 4. Hey, that's kind of cool. And this is a weird function, right? This is a crazy cos hyperbolic thing that we're integrating. But this, if you multiply that by 4, you get that. That by 4, yeah. We're going down by a factor of 4 every time we do twice as much work. So that says when I'm willing to do more work, I'm going to get a much bigger payoff with the trapezoidal rule than the left-hand rule. So less error to start with for a given number of intervals. And if I'm willing to do more work, I get far more benefit, far more accurate results using trapezoidal than left-hand rule. So it's a totally unambiguous. Trapezoidal is going to be a better approach. Which again, it makes sense. It matches and aligns better with what the function's doing.